We're going to kind of finish up the nomenclature talk since we're almost there at the end. And that is sort of the study assignment that we're going to kind of tackle for today. We're just finish up the last little bit here of naming. And then, like I said, you should be in pretty good shape in terms of the study assignment that you need to do. Okay, let's get it going here. Let's see here. Something to write with would be good. First off, though, is there any questions about naming so far that we've talked about? We've talked about type 1. We've talked about type 2. Again, they're both ionic compounds. Again, in both cases, it is the metal that's the most important. And again, if the metal is group 1, group 2, group 3, zinc, cadmium, or silver, then it is no Roman numeral needed or anything like that. You use the whole name of the metal, IDE on that non-metal name at the end. If the metal is a transition metal, or just to the right there, where lead, tin, antimony, all those guys are hanging out underneath that staircase, then you would need a Roman numeral in that case. Again, the Roman numeral is the charge on the individual metal ion, and you include that in the name. You can figure out basically what it is bound to, the charge there, and sort of work your way backwards. No, you will need to know the polyatomic ions. They won't be provided on the exam. So it is something you do have to know. So hopefully after today's lecture, going through that study assignment is going to be really good practice. There's a lot of naming in that one, and you should hopefully know most of these. So they will not be provided. You do need to know them. Other questions on that? Okay. Then we started obviously here at the end talking about polyatomic ions, which again, they are really groups of nonmetals that are together. They're really sharing electrons, but they do have an overall charge. So that's what makes them ions. And that's also why, because they are technically sharing electrons, that's why we do not see them like completely sort of fall apart into each of the elements or anything like that. They do move around as sort of a whole group and everything. And we typically will have our polyatomic ions hooked up with metals. And again, we will default back in most cases to our type 1 or type 2 rules, including for those metals, whether or not you need a Roman numeral or not. Same thing with our polyatomic ion. Even if there are more than one polyatomic ion in the formula, we still have no effect on the name. So I guess what I mean by that is, let me do one here just to kind of give you an idea. Let's say we had, since we got hydroxide here somewhere, right here. So let's say we had CaOH2, for example. And the name of this would be based off of calcium, which is group 2. So we would use the entire name of the metal. The OH is OH minus, which is hydroxide. Now, a couple of things about the formula and the name. Obviously, there's a 2 here. It does not have an effect on the name, just like kind of type 1 and type 2 guys. We just use the whole name of the polyatomic ion. Secondly, there's parentheses there, and that's because calcium is +2. Hydroxide is -1. So we need 2 hydroxides here to balance out the charge, gives you -2 and +2 in that particular case. And when we write it in the formula, and whenever you have more than one polyatomic ion, you do need to put parentheses around the polyatomic ion, basically to indicate that that is the unit. We have 2 of those units. You would not want to write it like this, because without the parentheses there, that means we have 1 calcium, 1 oxygen, and 2 hydrogens, which is really not what we have. We have 2 oxygens and 2 hydrogens. So that's why we do need to have the the parentheses there to indicate it. So one sort of aspect of When you have more than one polyatomic ion, you do need to put parentheses around it, the number on the bottom to indicate how many units there are. But even though you have more than one of those, it has no effect on the name. You still use the whole name of it as well. Any questions on that? Now, we don't use prefixes here or anything like that. The only time we would use a prefix is if the actual name of the polyatomic ion has a prefix, like dichromate. The dichromate is not a prefix for naming, is actually the name of the polyatomic ion. So that's the only time we would sort of have a prefix sort of creep in there. Any questions on that there? Okay, why don't we try some here, see how you do. Why don't we do some names on this guy here? Let's do and let's do some formulas on this side. Okay, so names on the left and formulas on the right. So take a few minutes here, see what you come up with. Again, refer back to the chart. It'll probably be helpful. Okay, let's take a look here and see. So starting on the first one, we see potassium here. That's a type 1 metal, and we have Cn minus, which is cyanide, which is a polyatomic ion. So really, again, when we have that metal involved, it's the important, and that would then be potassium, which would use the whole name there of the metal. No need for a Roman numeral because it's type 1, and this would be cyanide here. Any questions on that name? Looking at the next one, we've got Mn, which is a transition metal, manganese. That means that it can have multiple types of charges, which means it's type 2. So we do need to figure out what the charge is. Again, here we will know that OH is hydroxide, and there's 4 of them. So just very simply, you can just draw out all 4 of them. That obviously means it has a -4 charge. That means it should have a +4 charge to balance it out. We would use the whole name here, manganese, Roman numeral 4 for the charge. And again, even though we have 4 of these hydroxides, has no effect on the name. We just use the whole name of the polyatomic ion, which would be hydroxide in this case. Any questions on that there? Same thing here. We see copper, which is a type 2 transition metal. So again, might not know what the charge is, but we do know NO3 is nitrate, which has a -1 charge. And there's 2 of them. And that gives us a -2, which means this must be +2. And that would then be copper Roman numeral 2 nitrate. Again, even though there are 2 of them, we do also see the parentheses on each of these like we talked about, since there's more than one polyatomic ion, but again, has no effect there on the name. Any questions on that one? Down here, that's nickel, also a transition metal, so we'll need a Roman numeral. Following the same approach here, we do know ClO is actually ClO minus, and that is hypochlorite. And again, there's 4 of them, which gives it a -4 overall. Means our nickel should be +4, and our name should be nickel Roman numeral 4. And again, even though there's 4 of these hypochlorites, it will still be called hypochlorite. Any questions on the names, where any of the parts came from? So let's go the opposite way where we got formula or name. Let's do formula. So magnesium is group 2, so that's going to be a +2 charge. We also have hydrogen carbonate, which is one of those polyatomic ions, also known as bicarbonate, has actually a -1 charge. Again, even though there's a lot going on there, that whole thing has a -1 charge. That means we actually need 2 of those guys. And because we need more than one of those polyatomic ions, we would put it in parentheses with a 2 on the bottom there. Question on that one. And again, we do want to put the parentheses, otherwise you would end up with HCO32, and that would mean that you have 32 oxygens, which is, again, probably not what you're thinking in this particular case. Chromium Roman numeral 4 automatically tells us that the chromium does have a +4 charge. Sulfate is SO4 2-, so we are ultimately putting something with a +4 together with a -2. We need 2 of the sulfates to balance it out. So that would give us CR parentheses again, because there's more than one. And the 2 on the bottom in this particular case would be the correct formula. And lastly, ammonium sulfide. Ammonium is that polyatomic ion, which is NH4+. Sulfide is not a polyatomic ion. It is actually from the periodic table. It's IDE. It is actually just sulfur with a -2 charge. In this case, we actually need 1 more of these guys, and that's going to give us NH4-2S in this particular case. Any questions on polyatomic ions, how to handle them? Again, hopefully you can see, for the most part, because they're mostly negative, they essentially will follow very, very similar to type 1 or type 2 compounds. Any questions on that there? Okay. So the NH4+ comes first on the last one, because ultimately these are all ions here, so they're all ionic compounds. So 100% of the time when you're dealing with an ionic compound, either when you're writing the formula or you're naming it, it's always the positive guy first, followed by the negative. So always the cation, followed by the anion. So in this particular case, this is one of the few positive polyatomic ions. So it comes first in the formula, followed by the negative guy, which is our anion. Other questions on that? Any other questions on polyatomic ions there? Okay. So we're going to talk then about acids. Acids are essentially substances that produce H+ ions in solution. H+ ions are sometimes referred to as a proton. And they're referred to as a proton because, if you remember, hydrogen has 1 proton and 1 electron. It does not have a neutron, which means when it becomes positively charged, it loses an electron. So the only thing it has left is a proton. So sometimes referred to that. So when we go to name acids, acids are all about really oxygen when we talk about acids. And it's all about whether or not the answer to that question is yes, there are oxygen, are really there are no oxygens involved. So let's talk about the first case of an acid, which is no oxygens involved. So no oxygens in the formula or anything like that. When you have an acid that does not have oxygen in it, and by the way, before we get there, acids, essentially the cation is always H plus. So that's sort of what makes it an acid. Anion could be anything that's sort of negative. But whenever we talk about sort of an acid, it always is H plus is the cation part of it, the positive part of it. And if it does not contain oxygen, the acid will start with hydro something ic acid. So for example, if we have HCl, and what oftentimes makes something an acid is, and usually when you write formulas for acids, we oftentimes will include the AQ symbol next to it. The AQ symbol basically tells us it's a solution. It's aqueous is what that means. And really what that means is we're talking about something like HCl as H plus floating around in solution and Cl minus floating around in solution. And that would be different than if we had HCl that was, say, in the gas state. HCl in the gas state would actually be called hydrogen chloride. But when we take hydrogen chloride gas and sort of dissolve it in, and we dissolve it in water, it becomes an aqueous solution. And it becomes basically an acid. So when we look at this guy, we see definitely that there are no oxygens involved. And we would start with the name here as hydro. The middle part is the Cl here. So hydrochloric acid. So hydroic acid. We have something like HBr. That's aqueous. Also no oxygen involved. This would be hydrobromic acid. So hydroic acid. So oftentimes, sometimes when some people want to kind of name acids, they kind of always want to also throw that hydro in everywhere. So hydro is really just for acids that do not contain oxygen. So HCl would be hydrochloric acid, HBr would be hydrobromic acid. You know, you could continue on in sort of that pattern. Let's talk about acids that actually do contain oxygen though. So if we have some acids that contain oxygen, they will also contain something that everybody loves. Probably not. If it is yes to oxygen, it will contain a polyatomic ion. And if you remember, as we just talked about, those polyatomic ions, for the most part, basically end in one of two ways. They either end in ate or ite. And because they will be part of your acid, that is essentially how we will name the acid is based on whether or not that polyatomic ion ends in ate or ite. So for example, if it is, the polyatomic ion ends in ate, then the acid name will be something ic acid. And if we look at an example like HNO3, also we'll have that aqueous symbol next to it to indicate that it is an acid. And we would start with nitrate, ATE, becomes nitric acid. Like you ate too much, you feel icky is a good way to remember that. If the polyatomic ion ends in ite, ITE, the acid will be something OUS acid. So if we had something like HNO2, NO2 is nitrite. This becomes nitrous acid. So nitrous acid here versus nitric acid. Any questions on that? Okay. You will also notice that there is no hydro here at all. So definitely no hydro when your acid contains oxygen in this case. Any questions on acids? Why don't we try a few here? Why don't you give the names of these acids? Let's go with HI. Let's go with H2S. Let's go with H3PO4. Let's go with H2SO4. Let's go with H2SO3. Let's go with HF in this case, and maybe HClO4. All right, take a few minutes here and come up with the proper names for each of these acids. So this will be our no oxygen side, apparently. So no oxygen, again, going to start with hydro, going to end with ic. So this would be hydroiodic acid. Here, this is going to be hydrosulfuric acid. Again, here, you may wonder why we got two hydrogens and a sulfur. And it's because really what makes an acid, as I mentioned earlier, the cation's always the positive one, H, or H plus, I guess is a better way of saying that. But we're putting this together with sulfur, which is -2. So again, no charge we're looking for. So we do need that extra 2. So that's why there's a 2 here. No effect on the name, though, as you can see. So it's not like dihydrosulfuric acid, although that sounds kind of cool, but you know, it's not like that. So again, just the hydrosulfuric acid in this particular case. Same thing here, no oxygen on this side here. So that's going to give us a hydrofluoric acid. Any question on those names there? Okay, so won't always be broken up this way, I suppose, but we have on this side, though, we do have, yes, the oxygen. So remember when we look at an acid, and by the way, you can recognize these as acids because there are a lot of H's there, and there's all this aqueous sort of symbol that's there, tells us that these are acids. Again, here, when we do have that, we're going at polyatomic ion, and we're looking at whether it ends in ate or ite. So here we would really just look at this part of it since we know it's an acid. And that's going to be phosphate. And because that ends in ATE, our acid would be something ic acid. And that means that this would be phosphoric acid in this case. I see, again, no hydro here because there is oxygen involved. And again, you might be wondering why there are 3 hydrogens there. Again, the cation's H plus, the anion is phosphate, which is -3. So to balance that out, we do need 3 of those H's to balance out the -3 charge of our phosphate. Question on that one there. Here, same thing. We're going to kind of focus on the second guy there, which is SO4 2-. That is sulfate, which means my acid will then become sulfuric acid. Again, no hydro here because there's oxygen involved. Same thing with the H's. We have 2 of them to balance out the -2 that we got going on with the sulfate. Might look very similar, but it has one less oxygen here on this one, and that would be SO3 2 minus. That would be sulfite, ITE, which means my acid will end in OUS. So this will be sulfurous, OUS acid. And again, same thing here, because this is -2, we need not one, but 2 of these H's to balance it out to give us the proper formula. And lastly here, ClO4, that is ClO4 minus. And if you remember, the name of that guy is actually perchlorate. Since it ends in 8, that means my acid will end in ic, and you don't lose the front part either. So this becomes perchloric acid. This case, 1 H plus needed to balance out the -1 charge here. Question on naming acids or working from the name backwards. Any questions on that? So we didn't really kind of do one, but just, just to show you how you would, for example, work backwards from an acid name. Let's say we had phosphorus. I can spell that right, OUS acid. So if you had phosphorus acid, and maybe you didn't butcher the spelling like I did there, which is probably not good for a naming sort of lesson, I suppose, but what you gonna do, huh? So if we had phosphorus acid, a couple of things when we would be analyzing the name part here. First really big thing would be I don't see hydro. So because I don't see hydro in the name, that means that this guy should contain a polyatomic ion. That means it has oxygen, right? So then I want to think about, what does all this mean? Well, maybe I'm not sure, but I know OUS with no hydro means that my polyatomic ion should end in ite. And if I just kind of throw the front part of that on there, phosphite, so that means that is what I should be dealing with here and get the right charge, 3 minus, PO3, 3 minus. And then obviously always the acid cation is a +1 hydrogen there. So just kind of working the name backwards, now I got everything I need to put these guys together with no charge, means I need 3 of those guys. That gives me H3PO3. And again, you would put the aqueous next to it. And that's sort of how you could kind of work backwards from the name, use what's in the name to sort of help you out with that. So the one that was in the previous example, so your question was, in the previous example, we had NiClO4, and here we had HClO4. And sort of what is the difference between those two? The difference between those two is when we put the parentheses around this, the only part that's the polyatomic ion is that part right there. And if we pulled that out, what that really means is we have ClO minus. And not that the 4 is part of the polyatomic ion, but it means we have 4 of those ClO minus units. And the name of ClO minus is hypochlorite, which is why we named it, I hope, hypochlorite the last time. The difference is here, although it's basically 1 of each, and you don't usually put parentheses around it, this entire thing here is the polyatomic ion. And so this entire thing here, again, even though we don't usually put parentheses around just one of them, is the actual polyatomic ion. And that means that that is actually ClO4 minus. And that's why there's only 1 hydrogen here, because it's basically +1 and -1. And the name of this guy is perchlorate. So there is actually a difference between those two. For example, this guy is, the perchloride is this. The hypochlorite is like this in terms of how it's bonded, basically. So that's the difference between those two. Other questions on that? Questions on acids or anything like that? Okay. So now that we've named acids, we have just one more sort of thing to talk about, and that is going to be what is referred to as type 3 compounds. So all these sort of guys that come together here are really ionic. So now we can sort of move to covalent compounds here. And let us talk about those guys, which are type 3. So type 3 guys are different. They are molecular compounds. They're covalent compounds. They are sharing of electrons, basically. So we have basically two nonmetals. We have sharing of electrons. And the deal here is, you've been waiting for it all night. This is where we use prefixes. So this is actually the spot where you should use prefixes. These are really the most easiest ones to name and to really do, but they are the ones that people really screw up the most because they try to do all kinds of funky things. I think I said funky there. All kinds of funky things to mess themselves up. So the nice thing about this is there's no charging involved. There's no ions involved. There's no balancing charges. You simply just need to pick the right prefix and follow sort of the rules. So the rules basically for naming these guys are: the first element in the formula, you use the whole name. So whatever the first element is, you use the whole name. The second element gets the traditional nonmetal way of naming, where we add the IDE to the back end of it. The only additional thing that we add to perhaps both names, and not always, but to perhaps both names, is a prefix and a prefix. So let's talk about those prefixes. There is mono, which means one. There is di, which means two. There is tri, which means three. There is tetra, which is four. There is penta, which is five. There is hexa, which is six. There is hepta, which is seven. There is octa, which is eight. I'll go with nona. Why not? There's nine, and maybe I'm making it up, but it could be deca, which is 10. And these are the prefixes that we use along with the whole name of the first element, the IDE of the second element. There are a few rules, though, and a couple important rules when we're using prefixes are: we do not use mono on the first name, but it is okay on the second. And what sometimes does happen is we do get a couple of vowels that sort of back up to each other. So we typically will drop the vowel off of the prefix. So what I mean by that is, let's say we had CO, and we look at CO, that is carbon, which is a nonmetal. That is oxygen, which is a nonmetal. And as soon as you see that, you should be super happy, because there's like nothing really to figure out other than I should just use the right prefixes. So one carbon is mono, but we don't use mono on the first name. So we would call this just carbon because of that. There's only one oxygen. We can use mono on the second name. And if you just wrote it with the prefix, and then the next guy gets the IDE treatment, you would get carbon monoxide, which is not what we usually call it. And the reason for that is we got a couple of vowels that back up to each other. And this sometimes happens when we got like two O's happening. An A and an O is another one, two O's. And in that case, we typically get rid of the vowel off of the prefix. So we typically would get rid of this vowel here, and we would call this carbon monoxide. Would be the proper name here. Absolutely, positively no balancing needed or anything like that. Just simply proper prefix, and don't use mono on the first name. Drop the A if you got an A and an O. Drop the O if you got two O's. Actually, two I's seem to be okay. So people are okay with sort of the two I's. But that A and O and the two O's are very commonly, obviously, ones that we drop. They are, like I said before, really, the easiest ones to do, but they are really the ones that a lot of people will kind of screw up because they want to do all kinds of weird things with it. You simply just count what's there and you can name them in literally probably take 2 seconds, as these should really take you very, very quickly to do so. So again, the first element in the formula, whole name with the appropriate prefix, as long as it's not mono. Second element gets the IDE at the end of it, again with the appropriate prefix. And again, prefixes basically indicate how many atoms are present of that particular element. And here's again a prettier picture of our prefix table than what I wrote. And here's a couple of those considerations again. Here's one where we get the A and the O that backs up from tetra and oxygen. So we get rid of the A. And again, that O goes away as well. Now, there are things that really do just go by common names. H2O is an example of that. H2O is water. It is not a trick question. Nobody wants a refreshing bottle of dihydrogen monoxide. Doesn't sound so good. Probably why they call it water rather than that. So you should always use water for H2O. NH3 is another one. That's ammonia, not to be confused with the polyatomic ion we saw earlier, which is NH4 plus and has a charge. That's the ammonium ion. So different things. One has no charge. One is just called ammonia. Other one's the ammonium ion and does have a charge. You could add to that list. This one usually comes up as well. CH4. That is the simplest organic molecule you could have. That's our good friend methane is the name of that. Like when you light a Bunsen burner, the gas coming out there, that is methane. So those guys usually will go by their sort of common names, and you really shouldn't do type 3 on them, even though they are really non-metal. I touched upon it with the acids there, but hydrogen, even though it really is a non-metal, it is oftentimes treated more like an ion. And even though it's really sharing electrons, if we do have something where hydrogen comes first and a non-metal comes second, and again, it's not an acid, we just simply call it hydrogen and just chloride like we normally would. If you had H2S, which say is a gas in this case, not an acid, this also would be called hydrogen sulfide. So hydrogen is a little bit different. Again, even though there's a 2 here for hydrogen, it doesn't affect the name in terms of that. Again, if these were aqueous, these would be acids, and you would name them differently. So if you do have hydrogen that just comes before something and it's not an acid, whatever it may be, this would be hydrogen bromide. Any questions on that there? So even though technically hydrogen is a non-metal, because it really does become an acid pretty easily in these type of situations, it's almost treated more ionic than covalent, even though technically it's sort of sharing electrons. Any questions on that? Okay. So why don't you try a few here? We're looking for names, and then let me give you some names, and we'll look for some formulas here. All right, names on the left and formulas on the right. Something like that you need to do. So as soon as you look at this and you see I, which is a nonmetal, and you see O, that's a nonmetal, you should be happy. You just need to pick the right prefix. So prefix for 2 is di, and we do use the whole name of the first element, which would be diiodine. In this case, the 2 I's are actually okay. It's mainly kind of the A and the O and the O and the O that come together oddly. And then we have 7. Prefix for 7 is hepta. Oxygen then gets the IDE treatment, but here we are going to get that AO that backs up to each other. So we would call it heptoxide there without the A sort of happening there. Question on that one there. Same thing down here. We see C, which is a nonmetal. We see O, which is a nonmetal. Only 1 carbon to begin with. Prefix is mono, but we do not use it on the first name. So this would just be carbon. 2 oxygens. Prefix for 2 is di. And again, the second guy gets the IDE treatment there at the end. And that would be carbon dioxide. Any questions on that one? Same thing here. We got phosphorus, which is a nonmetal, Cl, which is a nonmetal. So we have 1 phosphorus, which prefix is mono. Again, we won't use it on the first name. So this would just be phosphorus. And we have 3 Cl's. Prefix for 3 is tri. And chlorine gets the IDE at the end of it. So phosphorus trichloride. Any questions on those 3 names? Now, I think almost the most easiest out of all of them is actually going from name to formula, because literally it tells you what to write. So as soon as you see a name where you see some prefixes like di and penta, that's type 3 all day. So di means 2, nitrogen means you write an N and a 2. Penta is 5, oxygen is O, you write an O and a 5, and you're done. No balancing, no worrying about charges. You simply just write sort of what's there. Question on that one. Carbon, which is a nonmetal with no prefix, but tetra is a prefix. So what we know about this is it is mono really, and there's only 1 carbon, which means you write a C. Tetra is the prefix for 4. And Cl is chloride, so CCl4, and you're done. And lastly here, di and tri, di meaning 2, tri meaning 3. So oxygen is O2, tri is 3, phosphide, and this made up thing O2P3 would be our probably made up thing. And that would be O2P3. And again, you know, type 3 is really sort of the simplest in that sense, but I'll be honest with you, people do turn it into the hardest because again, they try to do all kinds of weird things like balance charges that aren't there and those type of things. So non-metal, as you can see, and as you waited the whole day for, is the only place where you should be using prefixes. So to recap, at no time in any of these did I start naming something like iron Roman numeral 2 dichloride. There is no mixture of Roman numerals and dyes and prefixes in this type of situation. They don't come together. So everything has its specific time and place. Again, Roman numerals are only for type 2 metals. Prefixes are only for when you're dealing with non-metal and non-metals together. And you never want to mix them together. Otherwise, you should probably just mark it yourself and save me the time because it probably is wrong. Again, the only time you would probably ever see a Roman numeral and a prefix together is if you're dealing with a polyatomic ion that actually had a prefix in the name, like I mentioned earlier, something like this guy, which is dichromate. And that just happens to be the name of the polyatomic ion. So if I had Fe2 plus with it, and I had FeCr2O7, that would be iron Roman numeral 2 dichromate. And it's dichromate not because there's two of these, but it's dichromate because that's the actual name of it. That's the only place, you know, that you might potentially see those two things together. Pretty much in 99% of the time, if you're putting those things together, the Roman numerals and the prefixes, you're probably doing something wrong. So it is potentially possible to happen, but it would involve sort of a prefix that comes along already with a polyatomic ion that comes along already with a prefix that you might come across that. But other than that, you should really only keep these things really separated from, you know, what you're doing. Prefixes only type 3, Roman numerals only type 2, type 1 don't need either. No Roman numeral, no prefix. So everybody again has sort of their time and place in terms of the naming. Any questions on naming? That's like everything, I think, for the most part. I won't say everything, because if you do take 200B, all of a sudden they'll tell you how to name a whole bunch of other weird stuff in the transition metal chapter. But for the most part, this is everything you probably would need to name. Any questions on nomenclature, naming? Clearly, you need to be able to do these things. Yeah. Yeah, so the only Charlie, the only ones that are technically sort of transition metals that don't need Roman numerals, and they're not really considered type 2, guys, even though they're transition metals, is that zinc and cadmium, like we talked about. Even though they're transition metals, they do have fixed charges, +2 each, and silver has a fixed charge of +1. So I call it kind of like a backwards L right there in the transition metal region on the periodic table. And even though they're transition metals, they're actually technically classified as type 1 compounds because of that, or type 1 metals because of that, because they do have fixed charges. So even though they're transition metals, they have those fixed charges. So they really would be more classified as type 1 versus 2. Yeah, for the most part, it's just those three. Pretty much everybody else on the periodic table in the transition metal region and to the right will be more of a type 2. And that's why, for example, you had maybe something like this, Ag2S. And again, here, when we look at this, this is silver that has that fixed charge of +1. And that's why there's two of them to balance out the -2 of our sulfide. But because the silver really is a fixed charge guy, even though he's a transition metal, you do not use a Roman numeral with him. And that's why it's known as silver sulfide in this particular case. And the same thing with zinc. Zinc would look something like that, that one you asked about, ZNS. Same thing here. We only have one zinc because it's actually a fixed charge of +2 with our sulfur. That's a fixed charge of -2. And that's what gives us that ZNS. But again, even though it's a transition metal, it's always going to be +2. So again, you would eliminate the Roman numeral there because there's sort of no doubt sort of what the charge would be on those three. So for the most part, it's just those three that are transition metals that have fixed charges, and they're considered more type 1 metals than type 2. Other questions? You're welcome. And that's also why, for example, we might have come across this reagent or something maybe in a lab where you had something like this. And that's also why this is known as silver nitrate. And again, the silver here is +1 and the nitrate's -1, and it has a fixed charge. And that's why we don't call it something like silver 1 nitrate. Really, the whole purpose behind naming all kinds of naming that you do in chemistry is essentially just to tell people kind of like what you're dealing with, you know, what we're dealing with when we see a formula. And when we have something that has a fixed charge, is sort of a known property, like, okay, if I have silver, that's going to be +1, or if I have sodium, it's going to be +1 always. And it's not so certain when we're dealing, say, with something like a transition metal that can do multiple types of charges depending on the situation, you could have a copper that's +1 or +2. And that's why we specifically in the name of those type of guys, which are type 2, need to express the Roman numeral to tell people, hey, in this particular case, we're dealing with the copper with a +2 charge, for example, or the copper with a +1 charge. Other questions on naming in general here? Okay. So if I am not mistaken, that should wrap up naming. That also, believe it or not, I think should wrap up the information that's going to be on exam 2. Yeah. So I believe this is the last piece of stuff that's going to be on exam 2. We have, is it spring break next week, I think? And then exam 2 is after spring break. So I will go through obviously naming here.